and hi to all. I hope that you are in a safe place, in a good health. So today, as promised, I'm going to continue with our subtopics, which is about continues to do on the block direct mapping. So previously we have direct mapping, and now it is a block direct mapping. And under our cage there are several, I guess 4 if I'm not mistaken. Please check back, and you're going to see that there are few techniques that you can use. So block direct mapping is the simplest technique of direct mapping. Can map each block of the main memory into only one possible cache line. So if before this you have several cache line, right? So now for block direct mapping is going to be it's going to be one single line. And here are the standard format for main memory address and also cache memory address. So now you can see we have tag and we have block over here. So this is a new, previously you didn't have block, you have tag and also content. And no, you also have the what, tag online, and also the content itself. So here you have a block and words, and you can see the address format is to the power of n. And if let's say n is 2, so your address length is 4. Basically this one is quite similar to previous direct mapping. And you can see under a mesh memory you have the cache address and also cache words. So about the cache address, how it's going to be look like and so on, you're going to see it after this. And on the words, cache word is include the tag and also the word itself. So you can see tag and words is called as cache words, and the blocks only for the cache address. Let's remove. Okay, this one is just the pictures for the block direct mapping. You can have several. This one is we also already look in our previous slide, and this is the block by block, and how many words available. And you can see you have the memory address, and you can also have the tables or the picture look like this. You have this one is the block direct mapping. You have the line numbers. This is for the cache, and this is for the main memory. So you have the tag and also the word itself. Here is example. Given the main memory address format using the block direct mapping, so it's direct inform you what techniques that are using. If each memory words is 8 bits, so you can see what you need to do is to the power of what is going to be 8 bits. But you can see this one is also contents of each main memory words. So all in the main memory words is 8 bits. So of course you're going to do the total up later on. Same goes like previous subtopic, we have also the example look like this when you need to calculate the main memory capacity. How it is, I already shows you like the rectangles, how many inside is this L, let's say this one is N, multiple with this, you're going to get the total inside. Same goes to the mean memory capacity. Okay, let's take a look how we need to solve it. We have altogether is already give you in these questions 7 bits for tag, 7 bits for block, and 4 bits for words. Altogether it is 18 bits. Okay, this is the total memory bits. But when you want to come up with the memory capacity, these 18 bits, you need to change first to the words. Memory words is equal to 2 to the power of 18 because it is 18 bits, it's going to get as 256 kilo words. And upon of that, we have 8 bits. 8 bits, we're going to multiple with the total of the memory words, and you get lastly 2 megabits. And the block, you can see the block is 7 bits. And if you want to convert it to the words, you're going to put to the power of 7. And last question is total words. So you can see how many words that you have. Over here you can see this is the words, and total is to the power of 4. It's going to be 16 words. And please remember also the total words, where is it? Okay, the total of cache words is including the tag and also the word itself. So that's why you're going to cache word size is tag plus the word cache with the size. You're going to get 7 plus 16 multiple with 8. Why it's 7? Because it is tag. Tag is 7 bits. And of course this one also you need to change it to the bits. This is 16 words. And you know that it's going to be multiple with 8 bits. And all together we'll get 132 bits for the cache word size. This one is more like mathematical terms also. It's quite easy. And example 13. Consider the main memory address you were given already. And if let's say you want to calculate first how many totals of bits you have. So you have 14 bits all together, including your tag, block, and words. Suppose a program generate the address of 1AA. What is 1AA? So you need to convert it. This is in hexadecimal. So please try to convert it into the binary. So in 14-bit binary is going to be this value, but of course when you have all is 14, when you get only this one, this is only 12. and you're going to put 0, 0 in front as the padding to the MSB, as just to complete the question asking for 14-bit binary. So now you can see that later on you have the main memory address. So you will get 0, 0, because your tag will be 7, right? 0, 0, 0, 0, 0, 1, 1. Because this is occupy 7 bits. And another 4 bit, 0, 1, 0, 1. So this is 4 bits for block, and the rest 3 bits is for words. Okay, so you need to do the solution for it. If let's say, I think this one is the example previously, so it is not too hard. Maybe you can try it first. I think it's similar. And how about if let's say we have the example 14, cache hit. What happened? Suppose the program generate the subsequent address 1AB. So you convert lah. You convert to a binary. And if let's say you can see over here you have 1AA, what is happening on your main memory address? If 1AB, what will happen? So you have at the beginning 1AA is like this. And if 1AB, 1AB is what? So you need to come up with the value of the binary itself. And that's why if you come out with the binary, you will get over here is the padding that you add as just to complete and fulfill the 14 digits. 14, right? I think so. Okay, 14 bits. 1, 2, 12, 13, 14. Okay, good. And in the cache memory standard form, you're going to have your block, tag, and words. Word is to the power of 3. And you're going to also see you have all this tag and block. Block is 0, 1, 0, 1. Okay, this is block. And the tag is 0, 0, 0, 0, 0, 1, 1. The rest is 0, 1, 2, 3, 4, 5, until 7. All together is 8. From 0 to 7, its total up is 8. Now you're going to see your block is here is 0, 1, 0, 1. This is the block. And if you look 1AB, you're going to pick the 0, 1, 1 as the words of 0, 1, 1, and your block is 0, 1, 0, 1. So you can see this is 1, 2, 3. 3 bit is for the words, and another 4 1 0 1 0 or 0 1 0 1, this one is the block, and this is the words, and you have the rest as the tag. This is if it's under cache hits. And for the cache miss, you were given also this similar, but it is in 14-bit binary, and you were given the value. Okay, I draw it for you. Maybe later on you can read and try to figure out why and what it is. So over here is for the tag. So that's why you put this tag like this, block, and the rest is normal things, which is 0 0 0 0 0 1 0 1 0 and etc. So please try to do the exercise 6.2. Is it okay or not, and how it will be come out. First is the main memory address format, and second is cache memory with all word fields. So before we this one is before we end up this block direct mapping techniques. So you need to see the advantages and the advantages of the block direct mapping. So this is the technique is simple and inexpensive to implement, while there's quite quite a lot on the disadvantages. So you can go through and try to figure out what is this. Please find out what is the disadvantages. And before we're going to move to the next subtopic, I'm going to end up first the video. We're going to continue later on in the next video. So thank you for your watching, and please stay at home and be safe. Bye bye.